Welcome to the talk about the xOpat viewer. We decided to create our own solution because existing ones are typically suffering from visualization and integrability issues discussed later. This viewer is actively used in machine learning research, publications, and software deployment, namely at Massaryk Memorial Cancer Institute. But before going into details, let's recollect some information on whole slide imaging in the digital pathology. Traditional pathology provides diagnostics of tissues by inspecting glass samples containing thin slices of prepared tissue under microscope. In digital pathology, these samples are digitized in a process called whole slide imaging and subsequently inspected in dedicated software tools. Advantages of this approach include work flexibility, such as the work from home, easy communication, sample databases with metadata, annotations, proofs of inspection of samples, and easy to access patient history. Digitalization also allows arbitrary zooming, unlike microscopes. Digital inspection furthermore opens the possibilities of applying machine learning analysis, which in particular could help to speed up the work of pathologists. However, despite these possibilities, digital pathology is still facing many issues. The data are large and hard to store efficiently, and scans can vary in diverse formats and quality. Files need to be stored in pyramids to allow for efficient viewer navigation. Even today, keeping software architecture supporting digital pathology can be very costly, especially with commercial solutions. Finally, one of the largest issues is the lack of trust from pathologists, who are not used to the role of digital pathology in their field. The first problem we encountered with existing viewers is that WSI data is so large and complex to work with that historically the only standardized solutions are patented or proprietary. For larger WSI biobanks, a change in infrastructure is not a viable solution, and their architecture must be optimized for local requirements and budget, not for the viewer in use. We needed a viewer able to adjust to various, often ad hoc architectures. Commercial software is typically costly to adjust and inflexible. Ad hoc solutions usually consist of a combination of several software solutions, causing communication and compatibility issues, such as employing several viewers for different purposes. We wanted to have a platform supporting routine work of pathologists as well as researchers, so that it is easier for them to either share findings and communicate, or push forward analysis research to the clinical practice in the long run. AI can generate many raster data we needed to effectively visualize in arbitrary overlays. Most viewers are able to, if anything, render data from multiple image channels and limit visualization capabilities. We needed a platform able to visualize an amount of pyramidal files with the ability to easily create new visualizations or combine existing ones in new ways. In the first part, we described the xOpat viewer as a flexible visualization platform. In xOpat, we can render simple tissue images without adjustments, superimposed or one at a time. Each layer represents exactly one image. This is pretty common in most of the viewers. Atop image layers, we render data layers. These are always rendered superimposed, as they form a visualization goal, a description of an intention. Each of these columns represents one visualization goal. Only one goal can be shown at a time. The visualization goals specify the data and how they are rendered. Unlike with image layers, each data layer can access arbitrary amount of raster data files, independently of channels. Each layer also uses WebGL to render its visualization output, using so-called layer shaders. On the right side, we can see how a combination of single image layer and 3 data layers in a goal can look like. Depending on the configuration used, we could be here looking at anything between 2 to 4 image sources, as the viewer is flexible enough to support both channel and file level access. Moreover, the image layer could be missing and the tissue could be just another data layer, an identity. The layer shader is an interface with advanced capabilities, allowing us to easily design new visualizations with automated features such as caching, exporting, blending, data access, and user interaction. In the image, we can see built-in layer shaders that can be applied on data layers. Although we have been experimenting with other visualizations, in practice they were not understood well by pathologists, and we settled on identity, interactive GLSL code meant for visualization design, edge detector, opacity-based heat map for linear and diverging values, and more generic, a color map. One of the powers of this platform is the abstraction from user input. Each shader specifies constraints on variables on which compatible input controls are interchangeable. For heat maps or edge detectors, we can threshold with single or multi-range slider, allowing us to perform different visualization tasks. Another example might be turning the opacity heat map, which is by default based on a solid color input, to an opacity color map based on color map input, all without explicit programming. xOpat also implements a UI configurator allowing to design visualizations interactively. We unfortunately do not have the time to describe in more details, but you can find everything in our paper or in the viewer repository and its documentation. The second part will focus on data transfer optimization and viewer API flexibility. The idea of flexible viewer API extended on the OpenSeaDragon ability to work well with both standardized and custom image style fetching protocols. We improved the official OpenSeaDragon library to allow us to optimize the data transfer required for the visualization platform we designed. These improvements generalized the data pipeline. We then used the improved API to allow for serialized data transfer across files, which decreases a lot of communication overhead. One can therefore use an image server able to serve from multiple files at once, or let the viewer to fall back to an unoptimized standard transfer. With other services and metadata, such as user data, a generic integration is much harder. This is achieved using customizable metadata scheme, so that any metadata can be used and sent to the viewer, and components can query it. Metadata is then propagated to requests. The problem is that the integration usually requires at least some programming. Furthermore, plugins have to carefully follow API design guidelines. We tested asynchronous read and synchronous transfer, where data was concatenated into a single image, blue the group middle, or sent as a zip archive, green right. The university Wi-Fi was able to cope well with many requests sent in a short time, while a private Wi-Fi had obvious problems. Furthermore, both the image server and client browsers can become problematic with too many requests sent in a short time. Through the viewer flexibility and the plugin system, one of our goals was to use the viewer in different scenarios. xOpat through plugins supports storytelling or annotations. Advanced, analysis-related plugins are in development. Thanks to the relaxed API interface, xOpat is integrable into the architecture of your choice. It is also usable both for clinicians and researchers, as the session can define the workspace capabilities and features. It is easy to share your session with others through URLs and files, or possibly configure a server storage service. For example, some exported sessions are available in interactive examples in our papers. A truly interactive collaboration is not yet available. In the last part, we will talk about 3 use cases and the future work. Users can share stories that enable to animate both the visualization and annotation objects, text in this example. The storytelling plugin is used to animate the story of the use case number 1. Here, an analysis researcher views individual layers from files, a ground truth label provided by a pathologist, turquoise borders, a network prediction, yellow opacities, and a diverging XAI occlusion, in the top part drawn as an opacity heap map in red-green, and blue-green in the bottom right. Such visualization can help to spot misalignments, invalid model configurations, for example patterns in the data, and mainly inspect the data in a broad context instead of a few small patches. Here, for an unknown reason, a highly performant model failed prediction on a horseshoe-shaped tissue part. XAI methods can help in further understanding of the model outcomes. A second use case was a binary evaluation of a model performance by a pathologist. Since the evaluation was binary, the xOpat annotation plugin allowed for fast task completion. The plugin supports annotation metadata presets pre-configuration, which can be seen in the right menu. The plugin can generate visualization segmentations automatically, or draw and adjust annotations with a freehand tool, while having the ability to use 2 presets at the same time. In the third use case, the task was to evaluate whether the regions contributing to the classification of either cancerous or non-cancerous image patches can be classified to some previously estimated tissue patterns, and secondly, the relative frequency of such patterns in different cancer grades. Both tasks usually require error-prone and time-consuming pixel-level data exploration. Thanks to additional sampling layer in a tailored visualization, the pathologist could quickly locate regions with unambiguous classifications and evaluate the whole image with reasonable effort in a reasonable time. In the future, there are many things we want to focus on. The OpenSeaDragon library can be furthermore improved for better caching and rendering behavior. The discussions are already in the progress. Although the viewer tries to abstract from underlying services, we need to have a good image server. We want to continue in the data transfer optimizations, support for DICOM WSI, and bring forward advanced features. Such features include arbitrary tiling, or defining custom tile overlaps. It would be also possible to create virtual subsets of physical WSI slides. As of now, the viewer works mainly with pre-generated pyramidal data. We would like to have a plugin that connects to our machine learning pipeline and allows for interactive analysis. Such analysis is already available in many viewers. Furthermore, we want to support real-time analysis, where prepared models are applied on the fly on tiles delivered to the client. To improve trust, we would like to have an ability to connect to an offline running analysis job. Such connection would then prioritize the processing of regions present in the user viewport. For more information, please visit our web pages, the open source repository, or contact us. Thank you for your attention.